Today we're going to be doing October-November 2023 paper 21. Question number 1 says the elements phosphorus, sulfur and chlorine are in period 3 of the periodic table. Table 1.1 shows some properties of the elements phosphorus to chlorine. The first ionization energy of sulfur is not shown. So part 1 says complete table 1.1 to show the number of electrons in the 3p subshell and the total number of unpaired electrons in an atom of phosphorus, sulfur and chlorine. Okay, now phosphorus is 3s2, 3s2, 3p3, right? So the valence configuration is 3p3, this is 3p4, and then chlorine is 3p5, right? So phosphorus is neon and then 3s2, 3p3, so there's 3 electrons in the 3p subshell, sulfur is 3p4, and then chlorine is 3p5. The total number of unpaired electrons is 3 for phosphorus, 2 for sulfur, right, and then 1 for chlorine, right? Construct an equation to represent the first ionization energy of phosphorus. The first ionization energy is when 1 mole of electrons is removed from 1 mole of gaseous atoms to form 1 mole of gaseous 1 plus ions. 3 possible values for the first ionization energy of sulfur are given. Circle the correct value. Explain your choice by comparing your chosen value to those of phosphorus and chlorine. Now sulfur, if you guys remember, is an exception, right? It's below phosphorus and below chlorine, right? So phosphorus is 3p3, right? And then sulfur has a valence configuration of 3p4 in the 3p subshell, and then chlorine is 3p5, right? This is the configuration in the 3p subshell. So what you guys should remember is that there is a decrease from phosphor to sulfur. That's an exception in the trend. The reason we have this exception in the trend is because of spin pair repulsion, right? And in phosphorus, all 3 of these electrons are unpaired, but in the case of sulfur, you have a pair of electrons, so it's easier to remove. And then from sulfur to chlorine, right, that follows the trend. That just follows the trend. So across the period, as the nuclear charge increases, right, the nuclear attraction increases, the number of shells remains the same, shielding remains the same. So more energy is needed to remove the electrons from chlorine, right? So sulfur should be below both phosphorus and chlorine. So it should be below 1060. Okay, so that means that the ionization energy would be 1000 kilojoules per mole, right? It's below both phosphorus and chlorine. So now we have to explain why sulfur is lower than both. So we would say sulfur has a lower first ionization energy than phosphorus, right? Lower first ionization energy than phosphorus because one of the 3p orbitals, okay, one of the 3p orbitals in an atom of sulfur, okay, in an atom of sulfur consists of paired electrons, okay, consists of paired electrons, right? Therefore, the valence electron is easier to remove, right? The valence electron is easier to remove, okay, or requires lesser energy to remove due to spin pair repulsion. It's easier to remove due to spin pair repulsion. Okay, and then you also have to talk about why sulfur is lower than chlorine, right? So you can just say that Cl has a higher first ionization energy. Okay, it has a higher first ionization energy than sulfur, as it has a greater nuclear charge, right? It has a greater nuclear charge, okay, greater nuclear charge, okay, whereas the number of shells and therefore shielding are the same, okay, and therefore shielding are the same. Hence the valence electrons, okay, the valence electrons in chlorine experience a greater nuclear attraction, okay, experience a stronger nuclear attraction. Phosphide, sulfide and chloride have the same number of electrons, give the full electronic configuration of phosphide. So phosphorus has 15, but we have a 3 minus charge, so we have 18 electrons, right? That's the same configuration as argon. So 1s2, 2s2, 2p6, 3s2, and then 3p6. State the trend in ionic radius shown by phosphide, sulfide, and chloride. You have the same number of electrons, but phosphorus has 15 protons, sulfur has 16, and then chlorine has 17 protons, right? So your nuclear charge is increasing, whereas your shells and shielding and everything else is the same, right? Everything to do with the electrons or the electronic configuration is the same. Nuclear charge is increasing, which means that the electrons are being held closer to the nucleus, right? Electrons are being held closer to the nucleus. So the trend is that it decreases, right? The ionic radius decreases from phosphide to chloride. Okay, the reason why is because the nuclear charge, right, or the number of protons increases, right, whereas the number of shells and shielding remains the same. Okay, whereas the number of shells, okay, and shielding are the same, hence, okay, hence the valence electrons experience a greater nuclear attraction. Okay, hence valence electrons experience a greater nuclear attraction, okay, and are held closer to the nucleus, okay, and are held closer to the nucleus. So that means your radius decreases. A student does 3 tests on separate samples of aqueous sodium chloride. Complete table 1.2 with the observations the student makes in each test. So in test 1, a few drops of aqueous bromine are added. We know that bromine is a weaker oxidizing agent than chlorine, right? So bromine does not displace chlorine, right? So there's no reaction between bromine and chloride because bromine is a weaker oxidizing agent than chlorine, so there's no reaction here. So the observation here is no visible change, okay, no visible change. They also accept colorless to orange. The reason they say colorless to orange is because the bromine aqueous itself is orange and you're adding it to a colorless solution, okay? So the color change mentioned, the colorless to orange mentioned in the marking scheme does not refer to a chemical reaction. It's just talking about aqueous bromine being added, resulting in the colorless solution turning orange, okay? But in terms of reactions, there's no visible change, okay? The solution is just orange because of the bromine being added, all right? When you add concentrated sulfuric acid reacts with sodium chloride solid to give you HCl, okay? It reacts with solid sodium chloride to give you HCl, so you see white fumes, okay? But you won't see any reaction with aqueous sodium chloride, okay? The reaction between the halides and concentrated sulfuric acid is for the solid halides, okay? It's for the solid halides. So again, you have no visible change here, okay? You have no visible change. And then if you were to add a few drops of dilute silver nitrate, then you would see a white precipitate, right, of silver chloride. Okay, you would see a white precipitate of silver chloride. Now, one way to think about why you don't see white fumes of HCl, okay, with concentrated sulfuric acid being added to aqueous sodium chloride is because you have aqueous sodium chloride implies you have a dilute solution of sodium chloride, okay. So if you add the sulfuric acid to a solution that's already aqueous, you're essentially diluting the sulfuric acid. Okay, you're diluting the sulfuric acid, so you won't have that reaction. When you have solid sodium chloride, and you have concentrated sulfuric acid, right, the sulfuric acid is concentrated. Essentially, you have a high concentration. You have a high concentration of the sulfuric acid in the chloride, right? But if you have aqueous sodium chloride, the word aqueous implies that it's dilute unless otherwise mentioned. So that means that you're essentially diluting the sulfuric acid and you won't get a reaction. POCl3 shows similar chemical properties to PCl5. POCl3 has a melting point of 1 degree Celsius and a boiling point of 106 degrees Celsius. It reacts vigorously with water, forming misty fumes in an acidic solution. Explain how the information in part D suggests the structure and bonding of POCl3 is simple covalent. We have a relatively low melting point and boiling point, right, similar to that of water, right? So here we can say that POCl3 has a low melting point, okay, melting and boiling point, right? Okay, therefore it has a simple molecular structure, and then we know that it has covalent bonds because it undergoes hydrolysis, right? It reacts with water to form an acidic solution. We know that covalent chlorides react with water, okay? They undergo hydrolysis and form acidic solutions. We know it has a simple molecular structure and it has covalent bonds, okay? It has covalent bonds because it is hydrolyzed, okay, hydrolyzed by water. We know it's hydrolyzed by water because it's forming an acidic solution. The only time we get an acidic solution is if the compound has covalent bonds, so then it reacts with water, right, to give you an acidic solution. Okay, hydrolyzed by water to give an acidic solution. Construct an equation for the reaction of POCl3 with water. So POCl3 reacts with H2O and it would give you H3PO4 and HCl. Again, it says that the reaction is similar to the reaction of water with PCl5, right? Because POCl3 shows similar chemical properties to PCl5. So PCl5 reacts with water to give you phosphoric acid and HCl, hence POCl3 would do the same. To balance this, you have 3 chlorines here, so that would be 3HCl. And then here you have 3 plus 3, that's 6 hydrogens, so you would have 3H2O. POCl3 contains a double covalent bond between phosphorus and oxygen. Complete the dot and cross diagram to show the bonding in POCl3. Show outer shell electrons only. So POCl3 would be like this, right? We have a double bond with the oxygen and then we have single bonds with the chlorine. Okay, we have single bonds with the chlorines. So I'm just going to use dot for the phosphorus. So we have a double bond with oxygen, right, like this. And then obviously oxygen has 6 valence electrons. We've shown 2 of them here in the bond. We have 4 more. That's 1, 2, and then 3, 4. It's making a single bond with each of the chlorine atoms. Making a single bond with each of the chlorine atoms. Chlorine has 7 valence electrons. I've shown 1 here. So each chlorine has 6 unbonded electrons, right, like this. Okay, and then same thing here, right? We have to show all the valence electrons. And then phosphorus just has 5 electrons and all 5 of those electrons are bonded, right? All 5 of the valence electrons are bonded from the phosphorus atom. POCl3 forms when PCl3 reacts with oxygen. Table 1.3 gives some relevant data. So they've given us the enthalpy change of the formation of PCl3 and POCl3 as well as the bond energy of oxygen. Part 1 says define enthalpy change of formation. The enthalpy change of formation is the enthalpy change, okay, the enthalpy change when 1 mole, okay, when 1 mole of a substance is formed, okay, is formed from its constituent elements, okay, its constituent elements in their standard states, okay, constituent elements in their standard states. Now, if it was standard enthalpy change of formation, then the substance being formed also has to be in its standard state. Okay, so you would say a substance in its standard state is formed. 1 mole of a substance in its standard state is formed from the constituent elements in their standard states under standard conditions. But here they're not asking for the standard enthalpy change of formation, they're asking for just the enthalpy change of formation. So just the elements have to be in their standard states. Calculate the bond energy of PO in POCl3 using the data in table 1.3 show your working. So here's the data given to us in table 1.3. Now we have to calculate the bond energy of the P double bond O, right, in POCl3. We're first going to look at the enthalpy of formation of PCl3. Now the enthalpy change of formation of PCl3 is when you get 1 mole of PCl3, you get 1 mole of PCl3 from the elements, right? Everything over here is a gas. So everything here is a gas, so we can use bond energies directly. Okay, everything is a gas, so we can use bond energies directly. So let's balance this equation, right? We have 3 over 2 Cl2. All right. And then we also have the enthalpy change of formation of POCl3 given to us. That would be P plus half O2 plus 3 over 2 Cl2 gives us POCl3. This enthalpy change is given to us as negative 289. So this enthalpy change is given to us as negative 592. So one way to do this, is first write down the enthalpy change for each of these reactions in terms of the bond energies. Okay, so for the first reaction, right, again the enthalpy change for a reaction is the bond energy of the reactants minus the bond energy of the products, right? So we have 3 over 2 times the Cl bond energy, that's your reactant, and then we minus the bond energy of the products, so we have 3 times the PCl bond, right? And this enthalpy change is minus 289. Okay, this enthalpy change is minus 289. We don't need to worry about phosphorus here because it's given as P over here, right? And then for the second reaction, we have half the bond energy of oxygen that's given to us, right? When 1 mole of gaseous covalent bonds is broken. So we have half of that. We have half a mole of oxygen here. So we have half times the oxygen bond energy, that's 496. Then we have 3 over 2 times the Cl bond energy, right? And then we're going to subtract the bond energy of the products. Okay, again, bond energy of reactants minus the bond energy of the products. We have the double bond between phosphorus and oxygen. Okay, and then we have the 3 PCl bonds, right? We have 3 times the PCl bond. This is equal to negative 592. So now what we see here is that we can subtract the second equation from the first one. Okay, we can subtract the second equation from the first one. Okay, and then the 3 over 2 Cl cancels out, right? The minus 3 PCl, and then this becomes minus, that's plus 3 PCl. So those two cancel out, right? And what you're left with is minus 1/2 times 496, so that's minus 248 plus the P double bond O bond energy, right? So minus 1/2 times 496 is minus 248 minus P double bond O, so that's plus P double bond O is equal to minus 289 minus 592. Okay, minus 289 minus 592, so that gives you 303. So the bond energy comes out to 551 kilojoules per mole. Okay, so that's positive 551 kilojoules per mole. Question number 2 says barium hydroxide is a strong base used in inorganic and organic reactions. Figure 2.1 shows a reaction scheme involving barium hydroxide. State the variation in solubilities of group 2 hydroxides. The solubility increases down the group. For sulfates, it's the opposite. For hydroxide, it increases down the group. State what is observed in reaction 1. So in reaction 1, we have solid barium oxide, okay, reacting with water to give you an aqueous solution of barium hydroxide. So barium oxide is a white solid that dissolves to form an aqueous solution. So the observation is simply that the white solid, that's barium oxide, okay, dissolves, okay, to form a colorless solution. Suggest a reactant for reaction 2. In reaction 2, we're converting barium hydroxide to barium carbonate. For that, we can use carbon dioxide. Okay, we can use carbon dioxide. This is similar to what we do with calcium hydroxide, right? When carbon dioxide is bubbled through calcium hydroxide, that's lime water, we get calcium carbonate. So that's why the lime water turns milky. We get a precipitate of calcium carbonate with calcium hydroxide, right? When we react with carbon dioxide. Similar things happening here. You can react barium hydroxide with carbon dioxide to get barium carbonate. Identify A. So compound A forms when barium hydroxide reacts with ethanoic acid. So we have ethanoic acid reacting with an alkali, that's barium hydroxide. Okay, so we're going to get salt and water, right? So the salt here will be barium ethanoate. Okay, barium ethanoate. So we have CH3COO minus, right? We're going to have two of those and then Ba2 plus. Okay, so that's the compound that we're getting. Okay, that's barium ethanoate. You don't have to show the charges here. Okay, you don't have to show the charges, but you can. All right, and you can also identify the compound by name. Okay, so the compound is barium ethanoate. Barium hydroxide is made by the reaction of barium with water. Write an equation for this reaction. Barium reacts with water to give you barium hydroxide and hydrogen gas. And to balance this, we'll just have 2H2O. The mineral barytocalcite contains both barium carbonate and calcium carbonate. Both compounds decompose on heating. State which compound decomposes first when barytocalcite is heated. Now, calcium carbonate will decompose first because the thermal stability of the carbonates increases down the group. The thermal stability of the carbonates increases down the group. So a higher temperature is needed for barium carbonate to decompose. It's lower down in the group, more thermally stable means a higher temperature is needed for its decomposition. So calcium carbonate is less thermally stable, more readily decomposes. Okay, so calcium carbonate will decompose first because the thermal stability, okay, thermal stability of the group 2 carbonates, okay, of the group 2 carbonates increases down the group, okay, increases down the group. In other words, a higher temperature is needed for decomposition, okay. Construct an equation for the complete thermal decomposition of barytocalcite. The formula of barytocalcite is BaCaCO3 twice. So when we decompose this, we would get barium oxide, we would get calcium oxide, and then we will get 2CO2. Right? The carbonates decompose to form the oxides and carbon dioxide. Barium hydroxide is used to hydrolyze organic compounds. Okay, so here we're talking about hydrolysis reactions. Figure 2.2 shows the reaction of B with barium hydroxide followed by acidification. Draw the structures of the organic products of the process shown in figure 2.2. So here we have compound B, right? Compound B has a nitrile and an ester linkage, right? We have a CH3 bonded to a carbon, CH3 bonded to a carbon. That carbon has a C triple bond N, where it has a hydrogen, and then that carbon is bonded to a CH2, is bonded to a CH2, which then is bonded to a CO2 CH3. So COO CH3, right? This is compound B. We have CH3, CHCN, CH2, and then a CO2 CH3, CO2 CH3. Okay. Now, when this guy reacts with barium hydroxide, we first have alkaline hydrolysis, right? So the nitrile as well as the ester both undergo hydrolysis. Okay, they both undergo hydrolysis. Now the C triple bond N, okay, will give us a salt of the carboxylic acid, but then we're acidifying it, right? Because we're following up with nitric acid. So this nitrile will become a CO2H group. Okay, this nitrile will become a CO2H group, and then this ester linkage here, right, also undergoes hydrolysis. So this C double bond O again will also become a salt of the acid, which again after acidification becomes a carboxylic acid, and then this guy here will become methanol, right? CH3OH. So one of the organic products is CH3OH, right? That's methanol, because again that's hydrolysis of ester, so we get alcohol here, And then the other organic product, okay, the other organic product is we have a CH3. Okay, we have a CH3 bonded to a CH. This becomes a CO2H, right? The C triple bond, and then we have a CH2. Then we have a CH2. Okay, and then again we get a carboxylic acid group here, right? Because the C double bond O becomes a carboxylic acid. Okay, so that's your organic product one. These are your two organic products. So here we have question number 3, which says potassium chlorate is widely used as an oxidizing agent and to make oxygen gas. Okay, so this is potassium chlorate 5. Now, what is an oxidizing agent? It is a species. It is a species or a substance that oxidizes something else and itself undergoes reduction. Okay, oxidizes another substance or species. Okay, okay, and itself undergoes reduction. Okay. In other words, it gains electrons. Okay, gains electrons. KClO3 decomposes when heated. MnO2 catalyzes the exothermic decomposition reaction. Complete and label the diagram in figure 3.1 to show the effect of MnO2 on the decomposition of KClO3. So here's the reaction profile in the absence of MnO2. Okay, this is the reaction profile in the absence of MnO2, right? What would the reaction profile look like if MnO2 was present? If MnO2 was present, the activation energy would be lower, right? The activation energy would be lower. So this will be the reaction profile in the presence of the catalyst. Okay, this will be the reaction profile in the presence of a catalyst. Okay, so we can say that this is the activation energy with the catalyst, okay, with MnO2, and then this would be your activation energy. This would be your activation energy with no catalyst, right? With no catalyst. And then the enthalpy change, of course, would be the same, right? The enthalpy change would be the same. Okay, so this is the enthalpy change of the reaction that remains unchanged. When KClO3 is heated without a catalyst, KClO4 and KCl form. Explain why this reaction is described as a disproportionation reaction. Disproportionation reactions are where the same species undergoes both oxidation and reduction simultaneously, right? So you start with a single oxidation number and you end up with two different oxidation numbers for the same species. Now here chlorine is plus 5, okay, that's the chlorate 5 ion, right, ClO3 minus. And then in KClO4, chlorine is plus 7, okay. You can find that potassium is plus 1, chlorine, let's say, is X. We have 4 oxygens, minus 2 each, that's equal to 0, so X is equal to plus 7, okay. So the oxidation state of chlorine in KClO4 is plus 7, and KCl, chlorine, is minus 1. So here we can say that chlorine is oxidized, okay, is oxidized from plus 5 to plus 7 and reduced, okay, and reduced from plus 5 to minus 1 simultaneously. Okay, it's oxidized and reduced simultaneously. Molten KClO3 reacts with glucose. KClO3 melts at 630 Kelvin. At this temperature, both carbon dioxide and H2O are gases. Use the ideal gas equation to calculate the volume in meter cube of 1 mole of gas at 630 Kelvin and 1 into 10 to the power of 5 pascals. Show your working, give your answer to 3 significant figures. So here we're going to use the ideal gas equation. PV is equal to nRT. We want to find the volume in meter cube, right? Again, this equation we use SI units, so we're going to find the volume in meter cube. The pressure has to be in pascals, which is given to us. Let's just first rearrange this equation. So we have V is equal to nRT over P, right? The number of moles is 1. R is 8.31 joules per Kelvin per mole. That's the ideal gas constant. The temperature is 630 Kelvin and the pressure in pascals is 10 to the power of 5. And this gives the answer as 0.0524 meters cubed. Okay. 0.0524. The three significant figures. 5 grams of glucose reacts completely with molten KClO3. Use your answer to D part 1 to calculate the total volume of gas released at 630 Kelvin and 10 to the power of 5 pascals in this reaction. So here we have the equation given to us for this reaction. Right? We've been told that we have 5 grams of glucose that are reacting completely. So we have 5 grams. We can first find the number of moles. The number of moles is the mass divided by the molar mass. The mass is 5. The molar mass over here is, we have 6 times 12 for carbon, so 72 plus 12 is 84. And then 6 times 16, that's 96, so 180. This gives us the number of moles of glucose as 0.02778 moles. Now, if you look at this reaction, 1 mole of glucose, right? 1 mole of glucose gives us 12 moles of gas, right? It's mentioned in the question that at this temperature, carbon dioxide and water are gases, right? CO2 and H2 are gases. So 1 mole of glucose gives us 12 moles of gas. So we can say the number of moles of gas is equal to 12 times 0.02778. This is equal to 0.3334 moles of gas, and that means that the volume of gas is the number of moles times the molar volume, right? The molar volume at 630 Kelvin is 0.0524 meter cubed, right? That's the volume of 1 mole of gas at this temperature, 630 Kelvin. Okay. So again, the volume of a gas is the number of moles times the molar volume, right? At RTP, that's 24 dm cube, but here that's 0.0524 meter cube, right? So this would be 0.3334 times 0.0524, and that gives us the volume as 0.0175 meter cubed. The structure of glucose C6H12O6 is shown in figure 3.2. Complete table 3.1 to identify the number of primary, secondary, and tertiary alcohol groups present in the structure shown in figure 3.2. Now over here, this is the primary alcohol, right? Because we have a CH2, right? The carbon with the OH. The carbon with the OH is bonded to one carbon. So that's a primary alcohol. So we have one primary alcohol group. And then all of these are secondary alcohol groups, right? Because the carbon has one hydrogen and two carbons, right? This carbon is bonded to two carbons. This carbon is bonded to two carbons. This carbon is bonded to two carbons. And this one is also bonded to two carbons, right? If the carbon with the OH is bonded to two carbons, that's a secondary alcohol group, and then we have 0 tertiary alcohol groups, right? Separate samples of aqueous glucose are tested with the reagents shown in table 3.2. Complete table 3.2 with the observation for each reaction. Write no reaction if applicable. Now, since glucose has primary and secondary alcohol groups, it will be oxidized by acidified potassium manganate 7, okay, and warming. So the observation here will be purple to colorless. With Felling's reagent, glucose has this aldehyde group, right? We have a CHO. So we would get a brick red precipitate. Okay, we get a brick red precipitate with Felling's reagent, right? Because that's a test for the CHO group. And lastly, we have alkaline, aqueous, iodine, and warm. Right now, this is a test for either the CH3CO group or the CH3CHOH group. Okay, these groups have to be present in their entirety. So it's a test for either the CH3CO group or the CH3CHOH group. Now, if you go here, we don't have a CH3CO and we don't have a CH3CHOH either. Okay, we do not have any CH3CHOH group or a CH3CO group present. So here we would say no reaction. Okay? No reaction. There are many structural isomers of C6H12O6. Defined structural isomers. They're compounds with the same molecular formula with different structural formula. Okay, with the same molecular formula but different structural formulae. So here we have question number 4, which says compound C and D are alkenes with the same molecular formula, C5H10. A part 1 says give the systematic name of D. Now, to name D, okay, we first have to number the carbon chain. We're going to start with the side of the double bond, right? We want to give the lowest possible number to the functional group here, which is the double bond. Okay, the alkene. So we're going to start from the right. So we have 1, 2, 3, 4, right? So we have bute for 4 carbon chain, 1 ene, and then on carbon number 3 we have a methyl group. Okay, so this is going to be 3 methyl, bute, 1 ene. Explain why C and D do not show a geometrical or cis-trans isomerism. Well, in C, the carbon is bonded to 2 methyl groups, whereas in D, this carbon is bonded to 2 hydrogens, right? For there to be cis-trans isomerism, both the carbons in the double bond have to be bonded to 2 different things. So this carbon has to be bonded to 2 different things and this one. That's not the case in C, right? Because one of the carbons is bonded to 2 identical groups. Same thing in D. Both the carbons have to be bonded to 2 different things, right? But again, in D, one of the carbons is bonded to 2 hydrogen atoms. So they're 2 identical groups, right? So we can say in both C and D, right? In both C and D, one of the carbon atoms, okay, on the carbon-carbon double bond is bonded to 2 identical groups, okay, is bonded to 2 identical groups. Draw the structure of a molecule that is a positional isomer of C and D. So the way to think about this is C and D both have the same carbon chain, right? They both have the same carbon chain, but here the double bond is shown to the right, right? That's carbon number 1. In C, the double bond is in the middle, right? But then if we want to show a position isomer, okay, we're going to keep the same carbon chain. We're going to keep the same carbon chain like this, okay, but we'll show the double bond to the left. Okay, we'll show the double bond to the left. Okay, another way to think about this is we're simply moving this methyl group. We're simply moving this methyl group from carbon number 3 to carbon number 2. So this is 2-methyl bute 1-ene. Give the structural formula of the compound formed when D reacts with hydrogen gas in the presence of a platinum catalyst. Now this over here is compound D. Okay, this is compound D, right? That's 3-methyl bute 1-ene. Now in the presence of a platinum catalyst, okay, we're going to have the hydrogenation or the reduction of an alkene, right? So we're going to end up making an alkane, okay? We're going to end up making an alkane. We're going to get rid of this double bond, okay, and we're going to end up with 2 more hydrogens. We have to write down the structural formula. So that would be CH3, CH2, right? CH3, CH2, and then we have a carbon with a hydrogen and 2 methyl groups. So CH3, CH2, CH, and then we have 2 CH3s. C can form an addition polymer. Draw the structure of one repeat unit of this addition polymer. Now this over here is compound C, right, given to us. So again, if you want to draw the repeat unit for this addition polymer, first just going to write down the double bond like this, right? So we have the double bond, and then on this carbon we have 2 methyl groups. We're just going to write those above and below. We have a CH3 and a CH3, and then on this carbon we have a methyl and a hydrogen. So we have a methyl, CH3, and then a hydrogen, right? So that's your monomer, and then for the repeat unit we were just going to break the pi bond and then show the continuation bonds. Okay, show the continuation bond. So that's one repeat unit. Okay, that's one repeat unit. The mass spectrum of C shows a molecular ion peak at mass to charge ratio 70. The peak has a relative intensity of 48.7. The relative intensity of the M+1 peak is 2.7. Show that the information is consistent with the molecular formula of C. Okay, so first we have to show that C has 5 carbon atoms, right? We know that the ratio of the abundance of the M+1 to M, or the M plus peak, is equal to 1.1 N over 100, where N is the number of carbon atoms. So the intensity of the M+1 peak is 2.7. The intensity of the M plus peak is 48.7, right? That's the molecular ion peak. That's the M plus peak, right? And this is equal to 1.1 N over 100, where N is the number of carbon atoms. So here, if you solve for N, you get N is equal to 5. Okay, so that means we have 5 carbon atoms, right? 5 carbon atoms have a mass of 60, right? The mass to charge ratio for the M plus peak is 70, so that means that the MR is 70, right? Which means that 70 minus 60, right, is 10, and this implies that we have 10 hydrogen atoms, right? So that means that the molecular formula, okay, the molecular formula is C5H10. C and D both react with HBr. C reacts with HBr to form E. Complete the diagram in figure 4.2 to show the mechanism for this reaction. Draw the structure of the organic intermediate. Include charges, dipoles, lone pairs of electrons, and curly arrows as appropriate. So this is an electrophilic addition mechanism, right? So we have to show the partial charges on the hydrogen and the bromine. We're going to show a curly arrow from the double bond to the hydrogen. At the same time, we have hydrolysis of the HBr bond. So we show the curly arrow from the bond to the bromine, right? We end up with a carbocation intermediate. We have to show the positive charge on this carbon, right? Because if we got a positive charge here, that would be a tertiary carbocation. If a positive charge here, that's a secondary carbocation, right? The hydrogen will bond here. The hydrogen will bond to the carbon on the right. So we end up with a tertiary carbocation intermediate, okay? Again, remember the hydrogen bonds to the carbon with more hydrogens. The hydrogen bonds to the carbon with more hydrogens, and we end up with the more substituted carbocation intermediate. So this is our carbocation intermediate, and then the Br minus, right, donates a lone pair of electrons and bonds to this positively charged carbon, okay? And again, they've given us the final product here, so we know that we have to show the positive charge on this carbon on the left, okay? But even if this wasn't given to us, you should know that we're going to show the formation of the tertiary carbocation intermediate, okay? By default, you'll always show the formation of the major product unless mentioned otherwise. D reacts with HBr to produce F, a chiral bromoalkane. Draw the structure of F. Now again, this is the structure of D, right? This is the structure of D. That was 3-methyl but-1-ene. For the structure of F, okay, for the structure of F, right, we have this guy. We have the addition of HBr, right? Now again, the minor product is the hydrogen goes here and the bromine goes here, right? But that wouldn't give you a chiral center. The major product has a chiral center. The major product, hydrogen will go to the carbon with more hydrogens. The bromine will go on this carbon, right? So the bromine goes here, right? And we can see that this compound has a chiral center right here, right? This carbon is bonded to a CH3, this alkyl group here, a bromine and a hydrogen, okay? So this is the structure of compound F. Explain why the reaction of HBr with C and D produces different major products. Now again, with C, okay, you had a choice of the bromine going here or here, right? Here you get a secondary carbocation, right? Because this carbon is bonded to 2 carbons. Here you get a tertiary carbocation. So for C, the major product is the carbon that's bonded to 3 carbons, right? Will get the bromine. Okay, so we get a tertiary as opposed to a secondary carbocation intermediate. In the case of D, right, we have a choice between secondary and primary, right? We have a choice between secondary and primary. So the major product is if the bromine goes here. Okay, the major product is the bromine goes here, right? The hydrogen will go over here, and the bromine will go to the carbon that's bonded to 2 carbons. So we can say that for C, right, the major product, okay, the major product forms via a tertiary carbocation intermediate, forms via a tertiary carbocation intermediate, instead of a secondary, right? So we would say which is more stable, right? The tertiary carbocation is more stable than the secondary carbocation intermediate, right? And 2-degree carbocation intermediate, the carbocation intermediate. And then for D, right? For D, the major product, okay, the major product forms via a secondary carbocation intermediate, okay, which is more stable, okay, which is more stable than the primary carbocation intermediate, right? Primary carbocation. So in C you have a choice between tertiary and secondary, and D you have a choice between primary and secondary. The reason why is because when we talk about the stability, right, when we talk about the stability of carbocations, right, tertiary is more stable than secondary, which is more stable than primary due to the positive inductive effect, of the alkyl groups, okay, of the alkyl groups. C can be used to form H. One possible synthesis of H is shown in figure 4.5. Different portions of C are used in reactions 1 and 3. Some of the products are then combined to produce H. Figure 4.5 does not show any of the inorganic products of the reactions. So here they've shown a reaction scheme. Okay, they've shown a reaction scheme, and then they're saying this compound G and compound J react to form compound H. Complete table 4.1 with the reagents and conditions required for each of the reactions shown. Okay, so let's go back here. So they've given us reaction 1 already. Okay, so let's first go to reaction 3. Now what reaction is reaction 3? We're getting G and we're getting a ketone. So what are we doing to this alkene? What's a reaction in which we can make a ketone from an alkene? That's a strong oxidation of alkenes, right? We're rupturing this double bond and we're using hot concentrated acidified manganate 7, right? Hot concentrated acidified manganate 7, right? When we rupture the double bond, if the carbon on the double bond, if this double bonded carbon is bonded to 2 carbons, right, we get a ketone. So this ketone comes from here. And if the carbon is bonded to 1 hydrogen, again, if the double bonded carbon is bonded to 1 hydrogen, right, we get a carboxylic acid. So here we get CH3, and then this carbon becomes a carboxylic acid. So CH3COOH, right? So compound G is ethanoic acid. Okay, compound G is ethanoic acid, and then they've also told us that J reacts with G to form an ester, right? So H is an ester. Now we know that G is ethanoic acid, right? So this part comes from G, which means that compound J must be an alcohol, right? This must have been an OH group in compound J. This must have been an OH group. So compound J, what we're doing is we're replacing the bromine, right? We're replacing this bromine with an OH, right? We're replacing the bromine with an OH, right? So what do we end up with here? We get this compound, right? We have this and then we have an OH over here, right? And then this alcohol, that's J, reacts with ethanoic acid to give you the ester, okay? And then for reaction 2, we have to use aqueous sodium hydroxide and heat. Okay, we have to mention the solvent. It has to be aqueous sodium hydroxide, right? Because NaOH and ethanol would give you an alkene. Okay, we get an elimination reaction. That's the elimination of halogenoalkanes. Okay, so in reaction 2, we're converting a bromoalkane to an alcohol. So for reaction 2, we're going to use aqueous sodium hydroxide and heat. Okay, NaOH aqueous and heat. For reaction 3, that was the strong oxidation of alkenes. We're going to use hot concentrated acidified manganate 7. Okay, and then for reaction 4, that's esterification, we're going to use concentrated sulfuric acid. Okay, we're going to use concentrated sulfuric acid as a catalyst and then heat. Okay, heat mildly or gently, so warm the solution, okay, to make an ester. So reaction 3 is strong oxidation. We use hot concentrated acidified manganate 7. Hot concentrated acidified manganate 7. Okay, and then for reaction 4, we use concentrated sulfuric acid as a catalyst. Okay, concentrated sulfuric acid as a catalyst, and we heat mildly, okay, for esterification.